Okay, so continuing the problem we're doing the other day, I'm just going to redo a figure very quick. So this time we need to calculate what's happening in the flange. So if I do a figure, let's say this would be the flange. This would be the web. Okay, that should be in the middle. Didn't do a very good job. That should be in the middle, okay? And we found the neutral axis to be here. And what we're trying to calculate is what would be the moment of the flange. So this is the flange. All right, and if you remember, that distance over here is 3.3 inches. I don't have it with me. I think the thickness of the top was 3 inches. So this is 3 inches. Okay, so let's say this call here, this point here, A. And we know what should be the shear on top. It will be 0 because there is no surface to shear against. Okay, so the goal over here now is to find what would be the shear at point A. Okay, so tau sub A will be equal to the shear force times Q letter sub A divided by I sub T. So in this equation, what is V? I think V was equal to 12 kips, if I remember right. Yeah, so here, the value of V is 12 kip. So here we can say where V is equal to 12 kip. I is the one about the neutral axis. We calculated that one yesterday, 390.6 inch to the power 4. And now here, be careful, what should be? What should be T? Let me see, we forgot one thing here, I think. So this is the figure over here. Okay, let's move here a little bit ahead. So we need to substitute here in tau sub A. Oh, okay, so sorry. So really the only thing we are missing is the Q sub A. So where Q sub letter A by definition is what? Is Y dA, but we say was equal to the area times distance from neutral axis to CG of area. I'm waiting for that one, okay? You're gonna see what that is. That's why I'm waiting. Okay, because it's not that obvious. That's all right. So you could Q sub A will be equal to what? What is the area of the green area here of the flange? So it will be 12 times 3. And now the distance from the CG of this area to the neutral axis will be equal to what? So it should be equal to 3.3, correct? 3.3 minus so 3/2, which is 1.5. Okay, so now let me ask you something. If we had to do the same thing now here for the web, what would be the thickness? You'll probably tell me that the thickness is this one over here, no? Yeah? Okay, so, and that is what it is. So what is the thickness for the top one? It's not 3, what is it? Basically, we're taking the integral YD in that direction. But what is the stuff that is constant throughout the integration? Is the width over here, no? So really here, the thickness is 12 inches. Because it's not that obvious here, but if we move it to here, you will see that it will be this one over here, no? All right, that's why I was waiting. Okay, so now that means that, so that we found that the shear point A equal to V Q sub A divided by IT will be equal to what? 12 kips times Q sub A, which is 12 times 3 times 3.3 minus 1.5 divided by 390.6, and T we say was equal to 12. So now here, be careful. I don't have it here with me, but please do this calculation. But remember, do this calculation as it is. But remember, this is 12 kip. So I guess this will give you what? The 12 will cancel with this 12. So it should give you a small value. Does that give you 0.1659 if you do this calculation? So basically, I have a result here, which is 165.9 lb in square. But what I'm trying to say is that I think that this is not really equal to that, because I think I forgot here to multiply by, this is 12 kip, no? So that needs to be multiplied by 1,000, okay? So that's here times 1,000. No, 100, 1,000. And then I think you should get the 165.9. Is that correct? Okay. Okay. All right, so now be careful because it might get a bit confusing. I'm gonna go slow. So this is the value at this point here. So basically we know that at the top is 0 and at point A is 165.9. All right, let me go to the next page. So basically we know that on the flange, okay, we know here, at the top is 0. Now we know that here is 165.9. All right, that'll be inch square. Okay, so now remember, what did we say last time of the class is that you can have an if you have something like this, so this is your flange. So let's say you assume which is not, no, okay, not, you do not assume that, assume that the shear is constant throughout the cross section, even though you know that is not true. It's 0 at the top and it's 0 at the bottom. But if we use that equation, what do we have? You could say that the shear in that cross section should be equal to some average force, which will be equal to shear force on the flange divided by the area of the flange. This is just an approximation. This is approximation, okay? So in that case, if we know the shear here, this is 165.9, then in that case, we could just solve for the shear force on the flange would be equal to what? The tau average, which is, we assume is equal to the tau sub A times the area of the flange. What would be the area of the flange? What is this area over here? I mean, we did it before, is 12 times 3. So from here, we could find that the average force on the flange would be equal to 165.9 times 12 times 3. And this will give us that the average force on that flange is 5.87 kip. But remember, this is the approximation. Is it 5.97? Yeah. Okay, thank you. 5.97. I want to write it here, 5.97. Okay, in case it's not clear. Thank you for checking. Okay, but now again, remember, if that's really true, no, the real distribution, so let's say real or exact, so real, exact, should look like what? So let's see if I do here the same figure again. What do we know about the value? The value should be 0 at the top. And here we know it's equal to the tau sub A 165.9. And actually it should be some type of parabola. Okay, and I'm going to show you that, okay? What happened is that generally this is the way it's done, and you will see why. But if you do it in detail, you're going to see what you get. So I need to redo the figure over here. Did I go to the next page? No, probably I can do it here. So just try to go a little bit bigger. So this is our top flange. Here I'm just going to do up to the neutral axis. All right. So this time, instead of taking the whole area, I'm just going to take a piece of the little area here. We know this will be 12. This is 3. This is 3.3. And now let's say we just have a general Y star over here. And just for clarity, I know now it becomes more confusing, but it's going to help. Let's call that distance here to the bottom of the area Y sub 1. Okay, so if you remember, we said that the first area moment of inertia needed to be equal to y dA, and that we could simplify this. So you see, this is an integration sign, meaning that really what we're doing, we need to integrate throughout this flange over here. So from this point here to point A, okay? But this can be summarized as doing the area times on the figure, what would be the Y sub star. Okay, and if you want, this would be from point 0 to point A, where this will be 0 here, and this will be point A over here. Okay, 0 and point A. But this is equal to this. Okay, so what would be now, be careful over here. So what would be the area of the shaded green area over here? It will be 12 times this height, no? So it should be 12. Now, if you write this height over here in function of Y sub 1, that would be equal to what? Would be equal to 3.3 minus Y sub 1. Do you see that? So it's 3.3 minus Y sub 1 gives you this height over here, no? Okay? So basically, this will be your area. And now, that one's a little bit more complicated. Well, not really, but what would be the y star? The y star will be equal to what? So it's the distance from the neutral axis to the middle of the area, so it will be equal to y sub 1 plus half of this one. And we know this one is 3.3 minus y sub 1, and we just take half of it. All right? So this is the same as here. This is this height over here, we take half of it. That's the only thing I've done. Okay? And this will be the y star. So if you do this calculation, you get this is equal to 65.34 minus 6 y sub 1 squared. So now, you see that this is in function of y sub 1, no? Okay, so let's do something very quick. Since you have the calculators, let's check. What should be the stress, the shear stress at the top? It should be 0, no? Because there is no area. So can somebody do maybe very quick, what should be Q over here at y sub 1 equal to 3.3? How much is 6 times 3.3 squared? Hopefully it would be very close, if not exactly equal to 65.34, no? It's exactly that, no? So you see here, a way to check is to say, you know, Q of 3.3 is 0, no? Meaning what? That the shear at this point will be 0. Okay, so that's a way to check. So that's why the shear, the mathematics will give you that the shear is 0 at the top. Okay. All right. So now that we know Q in function of y sub 1, we can just rewrite the expression for the shear by using that expression. So basically we have shear in flange. All right, would be that sub A would be equal to V times Q divided by IT. So again, this will be equal to what? This will be equal to V divided by IT times Q that we just found to be equal to 65.34 minus 6 y sub 1 squared. So now let's not do the mistake. So if we do the numerical application, this will give us what? 12, 10 to the 3 divided by 390.6 times 12 times 65.34 minus 6 y sub 1 squared. So if you do the numerical application, you get that the shear stress at A will give you 167.281, if I didn't do any error, minus 15.361 y sub 1 squared. Okay, so let's do another check here, another very quick check. Not gonna hurt. Okay, previously, what did we find here for task of A? We said that it was equal to 165.9, no? Okay. 165.9. All right, so this is the, let's say, neutral axis. This is y sub 1. This is 3. This is 3.3. So if we want to check the value here at point A, what should be y sub 1 equal to? Let's say here, check. Again, I'm not going to have the value, but I should know the answer. If y sub 1 will be equal to what? 0.3 inches will be that distance, no? From the neutral axis. Can somebody do the calculation? But I mean, I hope that if it's not exactly the same thing, you should get something very close to 165.9. Is that correct? Okay, good, okay. Okay, so this time, instead of doing the assumption as we did before, that the stress is going to be like constant over here, we're going to take the actual distribution. So we do this. We're going to take the exact distribution, this one here. So basically, what does that imply? That we can say that task sub A will be equal to V flange over A flange. But this time, instead of taking the result of 165.9 as the value, we're going to take the whole expression. So we're going to say 167.281 minus 15.361 y1 squared should be equal to V sub F over A sub F. So from here, okay, I do the substitution later. So we can find that the force of the flange should be equal to 167.281 minus 15.361 y sub 1 squared times AF. Okay, so now what is A sub F? What did we say was A sub F before? We say it was 12 times 3, no? Okay, but if we need to write A sub F in function of Y, this will be equal to what? 12 should be the thickness over here. And then you will have here the height of this element. that would be what? Okay, guys, so here now the dy is that distance, but since this is in function of y sub 1, I'm trying to write this distance in function of y sub 1. So basically this dy will be equal to 3.3 minus dy sub 1. So if I write over here, substitute into this equation so that V sub F will be equal to 167.281 minus 15.361 y sub 1 square times 12 times 3.3 minus dy sub 1. Okay, so that's what I was doing here on the Maple file on the second part. 167.281 minus 15 times 12, 3.3 minus y squared. If I integrate this one between 0.3 and 3, we're gonna get that the value of the shear force is 7,216.582, or which will be 7.216 kip, okay? So I'm gonna write here integrating. Maybe I can find the middle step here. All right, let me try to do something here. I didn't simplify anything. Okay, so just write it as it is, integrating. So I'm gonna write everything. So we integrate here. Will be equal to the integral between 0.3 to 3.3 of 12 times 167.281 minus 15.361 y sub 1 squared times 3.3 minus dy sub 1, and this will give you that V sub F is equal to 7.216 kip. Okay, and I hope that you see that the limits of integrations here is because when we look at this one here, this is y sub 1, starts from here. This is 0.3, and this is 3.3, okay? The points are here. Okay, so summary. If we had the approximation, what do we have for V sub F? Was 3. No. How much was it? 5.87? No, 5.97, no? Okay, so again, what's important here is what? Is that if you do the equation for the average, you need to realize that what? That you're gonna be on the shorter side of the shorter side. Why? Because here you assume that this is kind of equal to an average. And in here you're assuming that it's going from 0 to a maximum value. Yeah. So that this one has the same area that this one you want, but it will go farther out. But obviously, in order to find this one, what happens is a lot more calculations, no? And you need to do the interval. But the reason I cover this again is for if you do designs, you need to be aware of that. Is that if you're taking the average of stresses, you might not be able to capture what would be the maximum value. Okay. I'm going to tell you right now, 99% of the time, people do hand calculations for shear. They will use the average. Okay. But what happens if you want to compare to the final element? The final element will give you which one? Closer to this one, no? So if you want to be able to compare final elements with hand calculations, you also need to know how to do the exact, which is something we'll be doing later, no? Compare with final elements. Okay, and now let's say shear force in web. So I'm going to do it very simple. I'm not going to do any big derivation. What do you know is the total shear going throughout the flange is, throughout the cross section is 12. What did we just derive? The shear flow going through the flange is, the exact would be 7.216, all right? But now what we could say over here is what would be the amount of shear going through the web. So in this case, it doesn't matter really the maximum or minimum value because it will give you the maximum value. I mean, if you do, then I can do I don't feel like doing the whole math again. So what would you have here? You should have here what? V equal to what? V flange plus V web. Okay, so what would that give you? That V web equal to 12, which is V, minus V flange. So now again, please give me the values because I don't have them. What would be the VW approximate? And what would be the V web exact? So basically one, you need to do 12 minus 5.97. So it will be 6.03. And the other one should be, that one I'm not gonna know, 12 minus 7.216, 4.784. Okay, and here if you want, I leave it to you as a homework if you want to show it, but if you look at the real distribution, how will it look like? It will be like this. probably here you will have a jump. And then if this was the neutral axis, here should be kind of, and then it should be something like this, I guess. And then at the bottom, it should go to 0. I mean, I'm not going to do the derivation again, but why here will it be a jump to make it higher? What was the T over here? Was 12, no? Remember, tau equal VQ over IT, no? And here what would be the T will be, I think was 4. So it should be a jump of 3 actually, no? From this value. So if you look at it, this one should really be like 3 times the value. And then you know the maximum is going to be at the middle or the neutral axis, and then it's going to go to 0 at the end because there is no shear at the top. Okay, so just like I mentioned yesterday in class, I'm talking about concept. Remember I told you that every single class you take, I mean, it's not here, in any school, any type of structure that you study, there is one assumption that is made, is that everything is valid for what type of structure? Structures that are long compared to the depth of the structure. Okay, so, and like I told you, something way to think about it. So if you have something long and not depth, what would be the way to break it? It will be to break it in bending, correct? So other structures will be weak and bending, but you're not going to try to break it in shear, okay? Because it will try just to bend it, all right? So really what's the most important when you bend something, what is it? To find the normal stress or the shear stress? To find the normal stress, okay? As we did with other finite elements. However, the shear stress is extremely important if, for example, you're going to do what? So let's say, yeah, let's say if you have a flange that you want to bolt. So, okay, let me start this section. So let's say will be build up members. So as an example, let us just consider the same cross section that we had before, which is the T section. And let's say, what would be the 2 ways for you to create a T section? So let's say we could have, yeah, let me change this. So what could be one way to do it? Okay, I'm thinking about this in 3D, okay? Just gonna do 1D, but. So let's say you need to build a T section. What would be one way to do it? You could take, I mean, I'm gonna talk about wood. Maybe it would be easier. You can take 2 planks of wood. And what can you do? You could put nails or screws over here, no? Yeah. So you could connect this one this way. Now, what could be another way? You could take, let's say this time 3 pieces. So it will be, here you have 2 pieces, here you have 1, 2, and 3 pieces, no? And you can choose to do what? To try to connect this one to the internal one, and this one to this one, and then you will be doing the same thing along the length of your cross section. So imagine that you need to do a design and somebody asks you, which one is better? What is the best way to build that cross section? Okay? What will be your answer? I don't know, okay? So the thing is that, how can we figure it out? So obviously, the answer will be, it depends how this structure will be loaded, no? So if you put the load in that direction, or you put the load in that direction, you might have different effects, okay? But in this case, what we're gonna assume is that, assume vertical shear force V. We have about 20 minutes, so I'm not sure I'm going to finish it. So let me give you some theory before, maybe next time we do the example, okay? I don't want to rush through the example. So in this case, there's two things we can analyze. One will be, okay, which one of these ones is better if you assume a vertical force? And the other one would be, what should be the spacing between those bolts, screws, or rivets, okay? Whatever connection you want. Or it can be welding points, okay? So let's say here S, the S will be spacing. Okay, so I'm gonna write over here. When analyzing, build up members and connectors or connections, okay? So connectors can be bolt, nail, weld, glue, whatever you can think of, okay? The engineers generally use instead of shear stresses, shear flows. So this is very easy now. So basically, what is the shear flow defined? Generally is the letter Q, and this is equal to the tau times T. So in that equation, Q is the shear flow, tau is what we just calculated, VQ divided by IT, which is the shear stress. And T is the thickness. So what are the units? And this is what might make sense over here. What are the units for shear? force divided by area times length. So what will be the unit? So here, force per unit length. Okay, so basically Q could be Newton meters. Okay, could be generally LB inches. All right, so now let's say you have a structure over here. So we do a figure. Doesn't matter which one you do. I'm still using the T cross section, but it's because the one we have. So the same figure as before. Let's say you have one connector here, another connector here. And S is the spacing. And let's say that you know that for this connector, that can be a bolt, a nail, whatever you want. This one can resist a certain shear force. So this is the V of the connector. This is not the V applied to the structure, no? This is the total force that you need to apply to this member in order to break it. So here, just think about the units. What should be the units of distance? What should be the units of the spacing? Should be distance, no? Okay, so obviously this needs to be related to the shear force of the connector. So this is V connector. What would be the units of this? It should be force. Yep. Now, if we divide this by the shear flow, what would be the units? So this is force divided by force over length, no? So this would just give us length, correct? Okay. So the spacing required will be the shear force that the connector can withstand divided by the shear flow produced by the loading. So next time we do an example, but I want you here to have an educated guess, all right? So I can give you an idea when you do the design. You can do calculations, but the important thing is to have a good intuition. So pay attention to this figure over here. The nail will resist shear when the force is perpendicular to it, correct? If you try to break this one to disconnect it, you're gonna apply bending to try to break this here, no? Will be bending, but for this element will be shear, okay? So this means this will be strong here in this direction, yeah? If this is a nail, what happens if you apply the force up? Will it be able to pull, what is easier, to break a nail or to pull it out of the wood? To pull it out, yeah? It's a lot easier than to break it. So imagine here that you have nails instead of screws. And like we say, assume that the shear force goes this way. Right, let me put it this way. I'm going to do it up so that it's more obvious. What could be a better design? This one, so the left one, or the right one? For you will be reversed. So it's on the screen. So will it be A or B? Okay, it will be B, because now the force will be totally on perpendicular to the nails, no? But is that, so now you understand here why this one would be better, even though it would be more complicated to build it, no? Okay, so next time we're gonna do an example exactly doing that. We have a structure, we have here a cross section, we give some values, and we say for a certain nail or bolt, whatever you want, what would be the maximum force for each one of these cross sections. So probably we try to prove right our intuition of today. Okay, so today we're gonna finish a bit early. I don't wanna start the problems.